Hi everyone. I'll do a audio sync clap right now, just to have enter scene. So welcome back to the channel. I'm Kid VHS, or Tommy the Brain in Space, or Made of Stars, or Lava Eater. Who cares, really? It's just names. I was thinking about doing a small video on the next step of the game, and if we check out the Readme file for the repository, let's have a look. This is riveting, me browsing the internet. Okay, Turbo Rocket Ultra on GitHub. I'm trying to make the screen, yeah. What's up with the name? What's the game? MVP, minimum viable product. Doing now, player damage, enemy attacks. Mechanics. As I've not explained to you, I have a philosophy when it comes to game development, and it's very important that you know that my philosophy on game development isn't worth anything, because I've never made a game. I just like programming games as a hobby, and I hope you'll be inspired to do the same, because it's a lot of fun. If it's a lot of fun, really. So I was thinking the other day, when is a feature done? What does a feature consist of, etc. for my game? And I broke it down to 4 parts: mechanics, graphics, audio, and polish. And graphics and audio are basically just presentation, and presentation can sort of blend into mechanics. It depends on the feature, obviously. But then in this particular case, if we go back to what we're doing right now, enemy play damage, enemy attacks, the mechanics, in just a few sentences, it says basically, when a player shoots, enemy attacks will have a cooldown. When they are within a certain range from the player, obviously, they will simply attack the player, and with some probability they will succeed. Blood must splatter. Blood must splatter is not part of the mechanics. That's the graphics. Health must be reduced. This is obviously part of the mechanics. And the player must be careful. That's part of the gameplay. Sort of, you want to avoid being attacked. There should also be in the mechanics here some way of handling death. Perhaps healing. Healing is not part of this particular feature because, well, I want to keep the features really small. When the player takes damage and the enemy can attack, we're done. But then we have to almost immediately go into, okay, how do I implement these mechanics? I'm using, for this particular game, and the code is available on GitHub, so you can check it out. I'm using something called Ashley. Let's have a look at that. Ashley. There we go. This is riveting again. Let's do just lib gdx Ashley. It's been sort of broken out of, yeah, never mind. This is the official entity component system for libgdx. I've read somewhere that the performance is worse than something. I don't know. I don't care. It tries to be a high performance entity framework. Okay. So what is an entity component system? Well, you can just Google the concept. It's basically only used in game development, or is it? Someone else is probably using it for something useful. There's also something called GamePro Programming Patterns. This guy. This is a very interesting online resource. This is a book you can read completely for free online, or you could buy it. It's a collection of patterns for game development, and it's very inspiring, like when you're sort of I do not have the corona. So I'm back talking to you guys. Here we go. There's this online book called Programming Patterns, where the guy goes in depth on like low-level game program patterns that are really useful for understanding why you would use a certain pattern or a certain method of doing something. And two chapters or sections you can read for this particular thing is the update method pattern and the component pattern, because that's basically what the entity component system is. It's a definition of systems. Entities are the things in the game. In my case, that would be sensors, objectives, obstacles, enemies in the form of zombies, and of course the players. But the entities don't actually have any properties or methods of their own. They only have a bag of components. So a entity is just a bag for components, and the components only contain data. In my case, there I've made some I've probably sort of done the pattern backwards sometimes, actually including some methods in the components. If I have, I should probably change that. And systems are the game logic acting upon entities that have certain components. So basically the game loop is an engine, the Ashley engine we have right here. And the Ashley engine simply you define a bunch of systems. So a system in my game is obviously the render system. The render system acts on all entities that have a transform component and a renderable component. It used to be just a sprite component, but I added a separate renderable component to be able to have different types of components for different types of rendering. It's not complete or perfect yet. I'm going to be tweaking that thing later, because we'll look into the rendering later. This is the enemy control system. And what we do here is, this is the enemy control system. It is an iterating system. Iterating system in Ashley simply means that given a family of entities, and the family is defined by entities having these components. So in this case it's the enemy component, the body component, the transform component. The body component and transform component are pretty similar. However, I've separated them because there might be entities that have a transform component but no body component. So the body component contains a box 2D body, and the physics system acts upon these bodies and updates the transform component accordingly to give us a smooth, like, where is this particular entity right now in the world. And the transform component together with sprite components are used by the rendering system to render any particular entity that has a sprite or other things. So the iterating system maintains a list of entities, and for each entity it will call this method process entity with the delta time in seconds since the last call. Now the list is simply an array of entities, so it is very fast, and I have no issue with getting 60 frames per second with thousands of entities. My blood splatter system, I've toned it down a bit so the blood splatter isn't around for very long, but I got up to 30,000 entities that were being rendered on screen without noticing anything on my very powerful computer. Phone performance might vary, and there's lots of things you can do to sort of reduce the number of entities, and you could also use a pooling engine. Then you have to construct your components slightly differently, and I think I will refactor the code to actually use that, because why wouldn't you? It depends on the type of game. If you're going to have lots of entities being created and destroyed all the time, you should probably use a pooling engine. Anyway, and this system simply, it this method is called with the entity, and then you have to get the component. So I get the enemy component, body component, transform component. I call a method called cooldown. There should probably not be a method called cooldown. I should probably just change the property directly, and the logic should be contained in here. Food for thought. And then I check the state. When the enemy component state is chase player, then we do chase player. And chase player is basically just calculate the position of the player, create a vector that sort of says what's the distance to this player, and set the direction and try to go there. And as you can see, it's actually not moving the enemy here, because after we have analyzed the state of the player, we do things like move the enemy. In this case, if we're chasing the player, we sort of move at a brisker pace for the zombie. The zombies are supposed to be kind of slow, and the player speed is slightly higher, so you could outrun the zombies, but you can't actually move while shooting, so there's a trade-off there. But the zombies are motivated by getting your brain, so they'll get moving if they find you. Ambling, they're simply moving in some direction until they get bored. That's what the cooldown is there for. They move until the cooldown reaches 0. When the cooldown reaches 0, they will start seeking. And when seeking, so if we check the amble method, actually it's pretty simple. If time remaining is less than 0, we go to a new state, seeking. And the seeking do I ever set the cooldown? Cooldown. Seek. So this one should probably set the cooldown somewhere. It does, I think. So when you sort of and this thing basically, it creates a scan vector, and the scan vector is like the direct direction we want the zombie to look in. And this is a semicircle, and I have a debug system that could sort of show you the radar stream traveling, and it just checks to see if it can find the player anywhere in this, and if it finds the player, it will start ambling again. Yeah, and here we have the like, okay, we didn't find the enemy, we didn't find the player, and we didn't find, it can actually also find a different zombie that is already looking for the player, chasing the player. Like a zombie has found the player and is following it. A different zombie gets close to it and sort of, oh, this guy is following the player. Then I will also follow the player. And that's what this is. I have some code for that here. But if we don't find the player and we're not supposed to keep scanning, then we go back to ambling. And this particular thing is the cooldown, so it will amble for between 5 and 30 seconds in some direction until it sort of the cooldown is reached, and we start seeking again, and sort of, so the zombies just randomly amble about in the game. But as you can see, this system is getting big. Actually, it's a lot of code, and we have some rudimentary state management. Managing state, in this case the state is actually just a basically an enum, but it's called a sealed class in Kotlin. So I can define these states and say, okay, given this, given that. And this is by no means an actual state machine. A finite state machine is pretty simple to implement, and there are plenty of examples out there to use, and libgdx also contains their own implementation of a finite state machine you can use out of the box. And a finite state machine basically says, here are the states and here are the events or actions, whatever you want to call them, that can move you from one state to another. So we could have a state called chase player, and when the state machine gets an event saying reached player, we move to some attack state or something like that. Pretty simple stuff. So I was actually thinking about having a state machine for all these zombies, and I started actually doing that. But one of the reasons I want to do game development is because I really like to program and I like to explore advanced ways of doing things and also cool ways of doing things. So I'm not gonna do this. I'm not gonna use a finite state machine, and I've been wrestling with the concept I'm going to use for quite some time. I'm just gonna check the thing if he uses behavioral. Yeah, here we go. Type object. No, this isn't what we're looking for. So what am I going to be using for the zombie AI or behavioral system? I will of course use decision trees or behavior trees. So let's go have a look at that. libgdx behavior tree, and let's go getxi. Yeah, here's the wiki for behavior trees. So what are behavior trees? That sounds a bit advanced. Well, lucky for you, there's this game called Project Zomboid. It's a fun game. I haven't actually played it that much. I own the game, but like everybody else in the universe, I own more games than I have. No, it's what's that site called? Gamma Sutra, right? Chris Simpson's. Yeah, I don't know a lot about Project Zomboid actually, but I do know that at least one guy working on the game explored the use of behavior trees for AI and wrote this excellent article on gammasutra.com. This is going into the description for the video. You can count on that one. I'll just leave the tab open and post it on the link below. So what are behavior trees? Well, they sometimes are called decision trees, but it's simply a tree you build, and oh yeah. So here's a good illustration of tree nodes. Basically, you have composite nodes, you have leaf nodes, you have decorated nodes, and leaf nodes, and these are they make up the branches of the behavior tree. So, like for instance, if you want to implement, let's see if he has a cool example of an actual, yeah. So here we have an example of a behavior tree that you could actually use in a game. It uses a composite node called a sequence, and the sequence is basically do all of these things until one succeeds or fails. The tricky part about behavior trees is knowing how to use success and failure in the behavior tree together with sequences and what they are. So the processing order for this particular order, yeah, a sequence does everything until it fails. So in this case, walk to door, succeeds, go to next. Open door, succeeds, go to next. Walk through door, succeeds, go to next. Close door, succeeds. Then the sequence is done and we exit the sequence with the status success. So you could have an AI, and this works good for a zombie obviously. Am I hungry? Yes. Succeeds. Do I have food? Yes. A success. Go to next one. No enemies around. Also success. Then eat the food. So any one of these could lead to this particular sequence failing. Am I hungry? Yes. Do I have food? No. Then the sequence would fail and you could move on to some other part of the sequence. We also have something called selectors. A sequence is an AND very aptly. It continues doing things until either they all succeed or one fails. A sequence will return fail at the first failure. A selector will return success if any of the children succeed and will not process any further children. So a sequence here could be walk to door, success. Yeah, the sequence, he's modified the sequence, sorry for holding up here. So we have a sequence, the sequence is still and, so it continues working while we have successes. Walk to door, succeed, go to next. A selector, okay, it jumps down. Open door, failure, move to the next. Sequence, okay. Unlock door, open door, failure. Smash door, might work. But if no one succeeds, this will fail and the entire sequence will fail. So you can see you can build pretty complicated behaviors. And if we move down here, we have this more interesting selector. It will try first by doing this sequence. Walk to door, work, selector, open, smash, okay. It tries to smash the door, doesn't work either. Then it would try to walk through the door, which fails because this is a sequence. Then the selector will jump down into this sequence, where it walks to the window, tries to open the window, unlock the window, open window, smash window, and perhaps smash window will almost always work. Then climb through a window and close window. And this works very well if you're making, like Project Zomboid is a zombie survival game where you run about, try to gather supplies and not die and get eaten by zombies. So this could be an interesting behavior tree for a zombie running about in your game and trying to find food, finding people, looking through windows, etc. So this is what we're gonna be using.